Hi, my name is Harrison, and today I will be talking about LabVIEW image analysis. LabVIEW image analysis is a component of LabVIEW that allows for the analysis of images from image files, videos, and live recordings. You can use it for a variety of practical purposes, such as shape or object tracking like in Module 3 from BMed 3110, or shape and color recognition. For instance, you can create an automated hemocytometer cell counter that is able to distinguish blue dead cells from the living cells. Let me show you a few of the tricks I picked up while working with this last semester. Okay, so here I've opened up a blank document. Hold up. So I've opened up a blank LabVIEW document, and we go into Vision and Motion, which is down here, and Vision Express. And you want to open up the Vision Acquisition and just plop one of those in. So you can open up a folder of images, and you could either choose a folder of images, a video, or a live cam. And for a single image, you want the single acquisition processing, and with a continuous image, you want the continuous acquisition with inline processing. The process is the same, but since we'll be working with a single image, we'll choose the first one. Now the second option is useful for video files and webcam recordings. So you just follow the instructions here. Real simple. Now the vision acquisition, which I just finished placing down, is what allows you to open the image in LabVIEW. We go back to Vision and Motion and plop one of the vision assistants in, which will allow us to modify and analyze the image. So I've gone ahead and opened up the first image I'll be using. It's just me holding up a bottle cap, a green bottle cap, and for this I'll be demonstrating the color location. So for this we create a template, and I'll be creating it from the bottle cap screen. I'll select that and press the OK and save it as a PNG file. And as you can see, it has the score right next to it right here. It detects the bottle cap, and it has a score of 987. And if we go into settings, we can see the minimum score it needs to detect the bottle cap, which is 800, and this is basically the threshold. And we can change the search strategy to whatever we desire. And I'll be opening up my second image, which is me holding 2 bottle caps instead of 1. And we'll do this again, but as you can see, it only detects the left bottle cap and completely ignores the right bottle cap. We can go back into the setting and change the number of matches to 2 matches, and also lower the threshold to see if that helps. So now we find 2 bottle caps. So for our third image, it's Kurt Vonnegut's Slaughterhouse 5, upright, and I will be demonstrating the color pattern matching, which is different from the color matching. So color matching only finds colors, while color pattern matching finds patterns with colors. And I'll be highlighting the eyes because this is pretty distinguishable. We get the red and the black and the yellow all together right here. I'll be saving that as another PNG. So as you can see, we can detect it right here. Now, since I'm going to be turning the book, I will search for rotated patterns, and I will search the whole 360 degrees, 180 plus or minus. Now I'm going to be opening up the rotated book, and as you can see, it detects the eyes again. Now I've already loaded this script because it's quite lengthy, and I've returned back here to the 2 bottle caps. So what I'll be doing now is I'll be filtering out everything we don't want so we can focus on these two bottle caps. The first thing we'll start with is a color plane extraction. Specifically, we're going to be extracting the green plane. Unfortunately, my hair is black, so that actually stays black. The second thing we do is, now that it's black and white, we can go into the black and white threshold and look for dark objects and set it so that it only detects objects that are a certain darkness. Once we set that threshold, the image transitions from grayscale to binary, which gives us a few more options. Now, we can use the advanced morphology to remove small objects. And another advanced morphology to remove the border objects. And this is really useful because it removes a lot of the small and the objects we don't care about. And one last advanced morphology to fill any small holes we might have. From here we can do circle detection. All of this is under the binary functions. So circle detection using a minimum and maximum radius that gets rid of all the larger circles, like one right here or one's right here. So we only have these three circles. Now we could also do a shape matching using this template that I've already done, and that'll match these two shapes quite accurately, and it gives them the center X and center Y. However, if the shapes tend to change, we can go on to a particle filter. If we want to be even more automated, we can use the bounding rectangle's width and bounding rectangle height to remove the objects that are greater than a certain size or less than a certain size in pixels. And I'll do the same thing for the height and the same dimensions, so I only get these two circles. Now I can go back to advanced morphology and label these two objects, and then go into particle analysis and find the X and Y locations of these particles. So basically their positions. Say that this was what I wanted. That I wanted to find the locations of this bottle cap and this bottle cap. So I can go into the controls and select under particle analysis the particle measurements in pixels and the number of particles detected. And then I click finish. Now this will update a bit. So LabVIEW just froze up on me, probably due to work on VLab. So I can't update it as I wish. But usually you'd have outputs that would correspond to number of particles, basically the outputs that would correspond to the controls that you selected. And from there, you'd be able to use the locations and plug them into the Pythagorean distance formula and find the distance between the 2 points. If you're recording the image, say live from your webcam, you'd be able to find the real-time distance between the two bottle caps, no matter how they moved. Finding the position of these bottle caps could have been done more simply with the first method I demonstrated, but this method explores image analysis concepts that can be built upon for more complicated image analysis problems, like Module 3 from 3110 for example. Thank you for listening, and I hope that I've been informative. Does any Dr. SE/TA have any questions?